Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 2-5 Extra Practice Number 1 solutions on graphing polynomials in standard form. To graph this polynomial, we must first find the roots, which means we're going to need to factor this thing so that we can set each factor equal to 0. So to start with, let's look for common factors. Now it looks like all of these are divisible by 2. In fact, let's make it a negative 2. Just so we can get this x cubed without any coefficient other than 1. That would be helpful. So if I factor out a negative 2, I'm left with x cubed minus 6x squared minus 9x plus, let's see, this is going to be 54. And now inside here, I notice that I've got 4 terms. So this is something we could try grouping on. So let me do a little more common factoring. These first 2 terms, x cubed and 6x squared, I can take an x cubed out of those. So I still have that negative 2 out in front of everything, so this is going to be a little bit messy looking, but I've got that negative 2, and now inside a big parentheses, I've got an x squared coming out of these first 2 terms, leaving me with an x minus 6. And then for these last 2 terms, we can take out a negative 9, leaving me with an x minus 6. And then we close the big parentheses. So inside the big parentheses, we've got this x minus 6 that can come out as a common factor. So we have this negative 2 out in front of everything. We have an x minus 6 that I'm factoring out of the stuff inside. And then what's left is the x squared minus 9. Not quite done, though, because this x squared minus 9 needs to be factored if we can. This is an a squared minus b squared situation, so I can square root both of these terms and basically do a plus b, a minus b. So we have the negative 2, we have the x minus 6, and now we have x plus 3 and x minus 3. And now we've got this thing fully factored. So that took a little bit of work, but now it'll all be worth it. Setting each of these factors equal to 0, we find that our roots are going to be 6 for that first parentheses, and then negative 3, and then finally positive 3 zeros out that last factor. So putting those roots on our graph, we've got negative 3 somewhere over here to the left of the y-axis. On the right, we've got positive 3 followed by positive 6. And let's also find the y-intercept while we're at it. Now this is a little bit easier. That's just going to be the constant that you'll have left over in the standard form version of this if you zero out all these other terms that have x's in them by plugging 0 in for x. So negative 108 is our y-intercept, and that's down here somewhere. Not drawn to scale, just making a sketch here. And now the end behavior, we're going to look at the lead coefficient of negative 2x cubed for the end behavior. This is a negative x to an odd power. It's the basic situation. So this is going to behave like a negative x, like a downward sloping line, at least in terms of end behavior. So we're starting above the x-axis and ending below the x-axis. And then finally, for the root behavior, we noticed, looking at our fully factored version of the equation here, we've got all single factors, or all single power factors, all single roots. So that means we are going to cross through all of our x-intercepts. So starting above the x-axis, we're going to cross through negative 3, we go through the y-intercept, cross through positive 3, come back down, cross through 6, and we end below the x-axis, which is in line with our end behavior that we established over here. To get started on graphing this polynomial, let's first factor this out so we can get the roots. So it looks like I can take out a common factor of negative 5, and that leaves me with an x to the 4th minus 2x squared plus 1. And now inside here, we're going from x to the 4th to x squared to a constant. So we have a middle term with an exponent half the lead term. This is basically quadratic form. We can factor this like a regular quadratic, only we're going to use x instead of x squared when we break this down. So just trying to factor this, I'm looking for factors of 1 that add up to negative 2, and really only have one choice, 1 and 1. They have to both be negative 2. So I can split this up into, let's see, this negative 5 is still there, and we have an x squared minus 1 and an x squared minus 1. Now I can split these x squared minus 1s up a little bit more. If I square root both of these, I can write, well, we have that negative 5, and then I can write x plus 1, x minus 1, basically a plus b, a minus b for an a squared minus b squared situation. And then I can actually do that again for this other x squared minus 1. We're going to get the same thing. So we've got x plus 1, x minus 1. And I happen to notice now that I've got things expanded out a little bit, that I have some duplicate factors. These x plus 1s I can put together as an x plus 1 quantity squared. So I have my negative 5, I've got an x plus 1 quantity squared, and then I have these x minus 1s I can do the same thing with. So x minus 1 squared. This is fully factored now. So at this point, I'm going to get my roots, whatever zeroes out these factors. So that's going to be negative 1 for that first factor and positive 1 for the other factor. Putting those on my graph, I've got negative 1 to the left of the y-axis and positive 1 somewhere over on the right for x values here. And then for the y-intercept, that's going to be this constant of negative 5 that you see in standard form. That's what's going to be left over if you plug 0 in for these x's. So negative 5, that's going to be down here as a y value. Now for the end behavior, we look at the lead coefficient, or the lead term in general. So that's this negative 5x to the fourth. That's a negative x to an even power. So that means this is going to behave like a negative x squared, like an upside down parabola, starting below the x-axis, ending below the x-axis. For the root behavior, looking at my factored version right here, and this is why it was important that I collect these duplicate factors so I could really see what was going on. Once I've done that, notice I have these two squared factors. These are double roots for both negative and positive 1. Since they're both double roots, we are going to bounce like a parabola at both of those x-intercepts. So starting below the x-axis then, we bounce at negative 1, go through the y-intercept down here, come back up, and bounce at positive 1, and then we end below the x-axis, just like the end behavior says we would. We're trying to graph this polynomial. Since this is in standard form and we need the roots, we're going to have to start by factoring this. As always, I look to see if there are any common factors I can take out at the very beginning. And I notice that all of these have at least an x to the third power. That's the lowest exponent there. So I can take out an x cubed, and that'll leave me with x squared minus 3x minus 40. Now I'm going to look to factor that quadratic that's left inside. I need factors of negative 40 that add up to negative 3. So let's run through our factors. We've got 1 and 40. That won't work. 2 and 20. Still not going to do it. 4 and 10, well, that's getting closer, but that still doesn't add up to negative 3. How about 5 and 8? Well, positive 5 and negative 8 would do the job here. So we have that x cubed we initially took out. We have an x plus 5, and we have an x minus 8. Setting each of these factors equal to 0 and solving, we end up with roots of 0 for that x cubed, negative 5 for the middle factor, and x equals positive 8 for that last factor. Putting these on our graph, we have negative 5 somewhere over here to the left of the y-axis, 0 is the origin, and x equals 8 is somewhere over here on the right. Okay, so for the y-intercept now, that's the constant, the invisible plus 0 here in the original. Also, if you plug 0 in for x, you get 0 back. All of these things giving us our y-intercept. Also, there's the fact that you already have an x-intercept of 0. Since that's also on the y-axis, it counts as a y-intercept as well. So 0 is our y-intercept. We don't have to do any additional graphing for that. We do have to look at the end behavior, though, and for that we look at this lead term, x to the fifth. In general, that is a positive x to an odd power. So that's going to behave like a y equals x kind of situation, an upward sloping line in terms of end behavior. So we're starting below the x-axis and ending above it. And now for the root behavior, looking at the individual terms here, individual factors, negative 5, our first x-intercept, that came from this x plus 5, a single power. So that's going to be just a cross-through kind of situation. And the next one at the origin, 0, well, that came from this x cubed, which is a triple root. So we're going to have to bounce, or not bounce, we're going to have to flatten through 0. Bouncing would be second power. Third power we flatten through. And then 8 is another single root from this x minus 8. So that's another situation where we cross. So now starting below the x-axis, we cross through -5, go up, come back down, and flatten through 0. Go down, come back up, and cross through 8. And we ended above the x-axis, which is what we anticipated with our end behavior. For this problem, we're trying to graph this polynomial. To do so, we're going to have to factor it so that we can get the roots. And to factor it, we're going to start by looking for common factors. So it looks like all of these you can take out at least an x squared, because that's the lowest exponent. And also, if you look at all these, they're all divisible by 4. In fact, -4 is probably even better. So let's take out a -4x squared from everything. That'll leave us with a positive x squared for that first term. And then 40x cubed divided by -4x squared, that's going to be -10x to the first. And then finally, for this last term, that's going to be a positive 21. So now let's look for factors of 21 that add up to -10, just trying to factor this inside a little bit more. So 1 and 21, definitely not going to work. 3 and 7 is the only other option. And -3 plus -7 would give us -10, so that works. So we've got that -4x squared out in front, and now we also have an x minus 3 and an x minus 7. Setting each of these equal to 0 and solving for x to get those roots, we've got 0 for that x squared, that -4x squared, and then x equals 3 for that middle factor, and 7 for the last factor. Putting those on our graph, 0 is the origin, x equals 0, and also y equals 0, actually. This is going to be the y-intercept, and we'll write that down in a minute. 3 is somewhere over here to the right, and 7 is even further to the right. So again, we also have a y-intercept of 0. And we know this because, well, I mean, we're also on the y-axis here. But also, if you plug in 0 for x in the original, that's going to zero out all these terms with x's in them, and then there's only an invisible plus 0 left over. So now looking at our end behavior, that's going to be determined by this lead term here, this -4x to the fourth. Since that is a negative x to an even power, that means this is going to behave like a -x squared, like an upside down parabola. In other words, we're going to be starting below the x-axis and ending below the x-axis. Now looking at our root behavior, we're going to look at the individual factors for that. We notice that 0, that came from this x squared factor, so that's a double root, meaning we are going to bounce at 0. And then 3 and 7, those both came from single power factors, so that means we are going to cross through those x-intercepts. So starting below the x-axis, we said we were going to bounce at the origin, and then come back down and cross through 3, and then cross through 7. And we are ending below the x-axis, which is where we expected to with this end behavior here.